is the product rule? If I have a first times a second, what is the product rule?
First D second. Second D first.
Second D first?
First plus first.
Plus first D second. Second D first plus first D second. And whenever I say D, what am I trying to say?
Derive.
Derive. Now, could there be different orders? Like when Kyle said first D second, was he wrong?
No.
No, not with the product rule.
But with quotient
As
rule
long as
comes-
you said it correctly for the second piece. First D second, then I need second D first. I just don't like it doesn't ring as well. But for the quotient rule,
You need
I need to be careful because the product rule, addition is
commutative.
But in the quotient rule, I don't have addition. What do I have?
Subtraction.
Okay, so with the quotient rule, I have a top over a bottom. How many of you guys made a product rule one? Made a product rule one?
I made
How many of you guys made a quotient rule one? It's like half and half. Interesting. Okay. Sorry, coming back. Just curious. Wasn't like a personality thing, although we could have had fun with that, and I pretended like it was. But if we had a top over a bottom, what's the rule? For the first derivative. Bottom D top?
Minus top bottom over bottom squared.
The bottom squared, is there any D going on? Is there any deriving going on?
No.
Now, on Friday, at the very end of class, I had you guys take a picture of that page. Why? Because it's a forever card. Why? Because we can memorize the derivative of tangent, the derivative of cotangent, derivative of cosecant, and the derivative of secant the same way you're supposed to have memorized the derivatives of sine and cosine. Which is why I'm making this a forever card, because to some extent, yes, you should just memorize it. It'll make life easier and faster and all that jazz. We're now up to forever card product rule 12, quotient rule 13, more trig derivatives 14. Forever card number 14. However, I told you that today I would quickly show you where they came from, because what do we know about last year in tangent of x and how we can rewrite him? Rewrite. That's right. Rewrite. How can we rewrite tangent?
Sine over cosine.
Yeah, we could do 1 over cotangent. That doesn't help. That uses another new guy. But we could make it sine over cosine, which are the basic building blocks of trig derivatives. If I can go back. Did I say basic building block and you guys out of biology? Anyway. Sine over cosine. They're the basic building blocks of all these trig rules. So, if you can remember derivative of sine is cosine, derivative of cosine is negative sine, guess what? You should never have an excuse of completely forgetting any of these trig derivatives. Completely forgetting. Doesn't mean you won't forget what's on the forever card. But you'll have a way to solve, because we can rewrite every single one of them, guys. How can I rewrite cotangent?
Kind of sine over sine. Cosine over sine.
I was thinking cosine over sine. We could do 1 over tangent. But with tangents, it's kind of tricky. I'm not sure where we're going to want to do that. How about cosecant?
1 over sine.
1 over sine. And how about secant?
1 over cosine.
Why did I have you guys review the quotient rule before I showed you where all these trig properties come from? Because every single one of them is a
Bottom,
quotient.
top and bottom.
Now, just a few of you are like, well, hold on. We're not to the reciprocal ones yet. We're over here. Why am I going to come and in a red pen draw little boxes and triangles?
So that you know what's top and bottom.
Yep, top and bottoms. Quotient rules all over the place. You guys ready? I'm going to give you a 30-second head start. Not that you have to have it totally done, but at least you can be practicing your quotient rule.
Yeah.
Bottom D top minus top D bottom. All over bottom squared. Remember, when we square a trig, isn't there a snazzy notation for that?
Yeah.
It's not super snazzy, but it can get tricky. If I'm squaring something like cosine, isn't it just cosine squared of x? Which technically means cosine squared. But this is what you'll see, and these are what they mean. You see, okay. Alright. Bottom D top is cosine squared. Minus top D bottom is a negative minus a negative sine squared, which is plus sine squared. All over.
Hold on. This D?
All squared. Because bottom, cosine, d top, derivative of sine is another cosine. What's cosine times cosine? Bottom d top is cosine squared. Minus top d bottom, sine of x times negative sine of x. Well, minus and negative is a positive. Sine squared. Oh my goodness, cosine squared plus sine squared is 1.
1.
Oh my goodness, and 1 over cosine squared is secant squared. Now we're going to memorize secant squared. You guys took a picture of it on Friday. It's in the forever card. Derivative of tangent will always be a positive secant squared of x. Tangent of theta, tangent of x, tangent of t, tangent of whatever's. Just careful, I'm not saying tangent of 2x. I'm not saying tangent of 3 theta. Just tangent of x. Is secant squared of x. So the bottom one isn't going to be too much different because it's bottom d top. Wait a minute. Sine of x times derivative of cosine is a negative, right?
Yeah.
So that'd be negative sine squared. Minus top d bottom, well, derivative of sine is a positive, so cosine squared still keeps the minus all over bottom squared. Well, uh-oh, they both have a negative. Exactly. If they both have, can't I just factor it out? And if I factor it out, what do I have?
Oh, 1.
Sine squared plus cosine squared is 1. But there's a negative. So if that's just 1 and I get negative 1 over sine squared, isn't that negative cosecant squared of x?
Wow.
Now right away, looking at those two facts, the derivative of tangent is secant squared, derivative of cotangent is negative cosecant squared. Does anybody, just something that pops, if you had to memorize it right now and I gave you a quiz on these two rules,
You see.
what's a way of remembering which one goes with which?
What the numerator is. So the s for secant goes with the s of sine, and the c of cosine goes with the c of cosecant.
Okay, that's one way. That's one way. What else do you see? That could be. We have sine with secant and cosine with cosecant, which is a little bit tricky.
Yeah, because it's opposite.
Think about what you know. Wouldn't it be, as far as what you know, now, Kyle, it's totally a way of memorizing it and go for it if it helps. But isn't secant 1 over cosine? So maybe that makes a little more sense mathematically speaking. If you were trying to do like a math way. I'm going to have a 1 over cosine and it's going to end up being 1 over cosine squared, secant 1 over cosine. Or, so technically the denominator is the more mathy way, but the numerator is the more just like, oh hey, it's a trick. S with S, C with C. My way's similar. I just look here. I do C with C.
Oh. And then
So then tangent's the other one. The other way of thinking about it is, aren't tangents and secants related in Pythagorean properties like back and pre-cal? Isn't tangent squared plus 1 secant squared? And isn't cotangent squared plus 1 cosecant squared? So maybe it's another way of thinking about it. Tangent usually goes with secants because they share the same denominators, and cotangents usually go with cosecants because they share the same denominators. What's a way of remembering the negative?
The derivative of sine. Oh no, never mind. It's opposite. Oh no.
Whoa. What would you, just seeing that, what would you assume is going to happen over here?
A negative.
Let's go find out. Ready? How do I take the... Just a couple of you amazing ones are like, let's rewrite it sine to the negative 1. I like where you're going, but stop. We don't know how to do that yet. So, quotient rule. Bottom d top.
Because of constant derivative of none.
Bottom d top, the derivative of, if I was to put my box in my triangle, right? Derivative of 1 is 0, we'll forget that. Minus top d bottom, well, all over bottom squared. Oh no! I can't make the numerator 1, but what can I do? Can't I rewrite the 0 minus cosine is negative cosine? Can't I steal one of the signs for that and one of the signs for this? What do I have? A cotangent and a cosecant. Is that a thing? Yeah, it is. Although usually, I think we normally rewrite it cosecant first and then cotangent. But guys, it's multiplication. It's all right. It's all good. Commutative. Whether you have cotangent and then cosecant or cosecant and then cotangent, that's always going to be true. Now there are ways of remembering, oh hey, and look, wasn't the negative there? Booyah! I think that's a thing that we can use as a trick. Any of the trig with C's are going to have, C, it's a negative. Just careful, because you spelled C with an S. You see a pattern over here though, right?
Yeah.
With tangents and cotangents. The cotangent is 1 over a tangent is 1 over a cotangent. They're reciprocals of each other and their derivatives look similar. They're just going to different functions with different positives and negatives. Without me even doing any work, can you guys see what happened with cosecant and make a hypothesis as to what you think this derivative will be? Let's see if math really does work as nicely as we think it does, especially with these functions that are similar enough. A secant?
Secant and a tangent.
And a tangent? With a positive or a negative?
Positive.
All right, let's see if you're right. Let's see if math is this nice sometimes. Bottom d top, oh, that's 0. Minus top d bottom. The derivative of cosine is negative, so minus the negative is a positive. All over bottom squared. Oh, I think, oh, yeah, that looks super similar, doesn't it? So I can put a sine over a cosine, and I can do times a 1 over a cosine. And is that tangent? Haha. And is that secant? Look at you guys. Are there patterns to the rules? And we say
Yes.
yes. Look at it. Tangent and cotangent, they both have their related Pythagorean guy because of their similar denominators, squareds. Check the sign. Cosecant and secant. They have themselves times the guy they're related to. Just because of how quotient rule works out. Just check the signs. But guys, I'll warn you. I have just a few. The very final, forever final of the year. I have kids messing up these trig rules. These trig derivative rules. They're so important. Not that every single problem uses them, but the AP loves to throw something and be like, I wonder if they know this rule. I'll throw that in there. Like you guys, you just made up problems, right? Some of you threw in, well, some of you were trying to be tricky, some of you were trying to be hard, some of you were trying to be nice. Some of you threw in e to the x, some of you threw in trig. Just imagine if you're a AP calculus person where it's like you have to make every single question count. Let's see if they know the product rule and see if they know secant. It'll happen. Yeah. So we don't want to get any problem wrong. At least not the ones that are the basic derivatives. If they're throwing stuff at us, you gotta be ready. All right, let's do some problems. Not tons and tons, because there's one more idea called higher derivatives. There's one more idea called higher derivatives, because if you guys have been noticing, I've been saying a little bit more today. The derivative, the first derivative. The derivative, the first derivative. Was there anything else besides the first? Is there anything else besides the first? First section.
Oh.
You're going to start seeing trig. So let's zoom in on the easy ones. Let's go back.
Are we combining?
Alright, let's play.
And are we combining rules now? Like this.
Oh, every time you learn new rules, it just keeps on growing. Yeah.
So
It's
now
like,
we
oh,
do-
you know that too? Hey, we'll give you one. Yeah.
Do a basic and
I mean, if we get to the exponential log section, like they might be mostly exponential logs, like e's and ln's and that sort of stuff. But you're still going to have trig randomly show up. You're still going to have power rule, product rule, quotient rule. Every time you see new rules, it's like, well, you have to remember all the old ones. You guys done?
yeah, sure.
No? You guys haven't gotten this mastery thing down yet? It's just negative 10 all over x cubed plus cosine of x. Don't be amazed, you could do it too. What did I do?
I do think just a power rule.
I power ruled? No, that's a quotient.
The left one.
It's a quotient. I have to use the quotient. It's the top and the bottom. What if you just rewrote? Can every quotient rule be rewritten? Technically, yes, but not in the way that you know how to solve yet. But are some just basic rewrites, just waiting? Check it. Did I bring down the -2 and make -10, and then it was -3, and have we realized a negative exponent is a denominator yet? Algebra 1 comes back to haunt you. Does it make sense?
Yeah. That does.
Are we okay?
Yeah.
Okay. But why wouldn't I want to rewrite this one?
I don't know how to rewrite sign.
It's not just an X to a negative, it's a don't. Okay, so we can simplify. Now, hold on. Let's just assume, it's okay, we can be kind of uppity for a second. We can be like, I never make mistakes, even though it's so false. For me to say that and for you to say that. But let's just pretend. Oh, those silly little foolish math students. What could some people do right now?
Take out an
Be
X.
like, yay! Right?
Oh.
Now, how many of you know that's horribly wrong? Just kidding. We all know that's horribly wrong because I just said it was.
Did you kill something?
Oh yeah, horribly. What if, this is someone that might be even slightly more informed. They see the plus and like, oh no, I can't just take out the sign, that's horribly illegal. But they do see, ready?
Take out an X.
Look, there's an X there, there's an X there, there's an X there. Let's talk about sin. No, let's not. I mean, we can, but not right now, and not like that. No, my tangent T people. My tangent T over T, the limit. Who took out the T's? Let's not get tan. Oh, she wasn't the only one. There were plenty of others. John. But it happens! Because it's like, oh, there's so many X's, and you know your math, and you want to get rid of stuff, and there's nothing to do. So stop. I have a box, and I have a triangle.
Oh my god.
The basic math kills you. Multiplication, addition.
Oh yeah.
There we go. It is what it is. We just laugh about it and say, well, good thing the world's not resting on me to be perfect, right? Okay. Why am I going straight to derivative? Because guys, there's no rewriting. Bottom D top. Minus top. D bottom. Remember, only take derivatives when it's their time. Oh, there's some life lessons in there. Sometimes you just gotta wait until it's the right time. That's good. Good job, Ava. It's okay. Bottom D top minus top D bottom, all over bottom squared. I think we should just box it and be done. No, some foolish math students, it's okay, let's make fun of ourselves, but we'll make fun of them. It sounds nicer, at least it doesn't totally crush our self-esteem. Some foolish math students, what might they do?
Cross out extra.
Ah, look! Hey! What did they not pay attention to?
Hello.
Negative.
There's two terms and this is not shared. Illegal, 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 illegal. Poor little kittens dying everywhere. Resuscitate them, they're back. Alright, so. Well, don't even think about starting to cross out little X's. Alright, so, bloop, bloop. What can we do? Well, not too much. If I were you, I would never FOIL the denominator. Kind of like with limits, when we never multiplied out the denominator because we wanted them to stay factored. Same thing here. We want to get simplified as much as we can what's up there. For instance, I see distribution. I see something like an x squared cosine of x. I see a sine x cosine x. I see a minus 2x sine x and a minus sine x cosine x. See why I did that?
Yep.
This is legal, an addition and a subtraction. Those cancel when they're matching, when they're like terms. Technically, I see one more thing we can do. It's not going to make it much nicer, but it will be possible. What's one more thing they could do? Looking at what's left. Yeah. I usually get out a green marker whenever it's starting to get really nasty to show you what's left and say, is there anything in common?
Yes.
1x from the front, right? 1x from the front. Now, anything simplified. Come on, keep it legal. Be more confident.
Yes.
Wait, why'd you just change your answer? Why would I tell you to be confident about a wrong answer?
I'm gonna.
Ugh. It's okay. I'm not dogging on people that think there's something to simplify,
Oh,
but
so-
I just need someone to realize it's confidently, absolutely not able to be simplified in any
Okay.
way, shape, or form further.
So when you say confident, you made me seem like I was wrong. So
No, I said be
yes.
confident. I heard like a no in the back.
No.
No! Why?
By no means.
Can this factor doesn't match with that factor?
No.
No. Can I pull out anything else?
No.
There's an x and a 2. They are not the same. There's a cosine of x, sine of x. They are not the same. I got nothing. We're working on our basic algebra. It's alright. It's not basic algebra. It's like basic algebra 2. Okay, so I would love to do that, but I said there's one more concept, right?
Oh.
Don't be overwhelmed. Because
Good.
check out the chart. No. All you gotta do is just write down a couple and then there's a pattern. As long as there's differentiability and non-trivial. Oh, there's trivial derivatives. That sounds fun. Trivial things we don't have to do, right? Oh, nice. We can keep taking higher order derivatives as long as there is as long as there is differentiability and non-trivial derivatives. Sorry, we can keep taking higher order derivatives. Now we can, but just because we can do something, does that mean we should? No, it just says we can, if asked, if called upon, if the time is right. But not just randomly because you feel like it, because you can. Hey, life lesson is there. As long as there's differentiability and non-trivial derivatives, we can keep taking higher order derivatives. Doesn't mean we should, just that we can. So if called upon, if necessary, if asked for, if referred to, can you know what these are? All you really need to see are the first 4, because if you see the first 4, the pattern just continues. So I'll show you this whole little chart down here. But the pattern is, shout out to Newton with his little prime notation. Yes, okay, you can do y prime, y double prime, y triple prime, but you're not going to see that. What you're going to see, at least for our purposes, are these ones. You won't usually see any of the other columns. I'm going to zoom back in by making sure you guys saw higher derivatives. We can keep taking derivatives as long as there is differentiability, aka they exist and they're not trivial. But the notation is, just say first, second, third, fourth, and then the nth derivative, however high we need to go. On the AP last year, I think the highest one they saw was 27. Oh. There was a pattern, and we should have found the pattern. They didn't have to take 27 derivatives. Silly goofs. But y prime, y double prime, y triple prime. But you can also use numbers, like the 4th derivative, or 5th, or 6th. That can be in the function or in the y. This starts getting weird, and I'll show you why this is what it is another day. But there is dy dx for the first, and it starts getting a little weird after that. You can also say, take the first, take the second, get to the second, get to the third, get to the fourth. And I had a question. John? No, you good? Remember how I said we can? That doesn't necessarily mean we should. Right? Has there been a forever card that has referred to a time when maybe we will be asked to take a second derivative? And it's called acceleration, right? And it's called acceleration. Acceleration needs a second derivative, a y double prime, an f double prime, a d squared y over dx squared. Means a d squared over dx squared taken of position. Long story short, do you need to memorize this? No, it's just something to be aware of. Is that cool, guys?
Yeah.
You don't need to memorize, just need to be aware. Once you guys have the first couple written, you probably have the pattern for the rest. So just to end off class today, there is technically at the very end of homework, I believe, some word problems that say, oh, you know how to take second derivatives? Let's go deeper. So please remember your motion forever card. Please remember your problem solving tricks of pull out the most important information, take the words, figure out the situation. What are they really asking for? play with them. But what I'm most going to be paying attention to for tomorrow is if you got all the way up to and attempted the word problems. Sound good? As far as homework turning into Google Classroom, they got all the way up to and attempted word problems. Meaning, did you just see the words and stop?
Oh, no, we don't do that.
Did you get to the words, analyze what was there, do the best you can, and if you got stuck, put a question mark and move on. Does that make sense? So this one actually told me that I can and I should find all the higher derivatives. I say, okay, let's go. F prime, 15x squared plus 14x. Why am I going? Just because I can? No, because they told me to. 30x plus 14. Why am I still going? Because I can? No, because they told me to. 30. Why am I still going? Because they told me to. Now I can use a Roman numeral, 4. Or I can do a little 4 in parentheses. They always put parentheses. But why am I going to stop?
There's no derivative.
It's a derivative of 0, derivative of 0, derivative of 0, derivative of 0, derivative of 0. Hey, they're trivial at that point. All right, cool kids, get out of here. Toodles.
Chapelle.
Chapelle? Ooh, I'm going to a French one today. See you guys later.